This is a booklet I made for my granddaughter to keep her occupied during the lockdown. I made another one before, that was a triangle book as well, but that was describing the types of triangles, scalene, equilateral, isosceles, and right-angled. This booklet describes how we compare triangles. If we look at these two triangles here, they're exactly the same. If I move this one across to here, you can see that these are exactly the same. Same angles, same sides. They're the same type of triangle. In these two triangles, the angles are the same, but the sides are different. You can see they're the same shape, very similar, but not the same. And these are similar triangles. Looking at triangles, when we compare them, we look at the side opposite the angle. So the opposite the angle there we have side A, opposite this we have side B. That's how we compare similar triangles. Here's some more examples of similar triangles. These two, for example, look the same, but they aren't. They're similar, but as you can see, the angles are the same, but the sides are different. They're similar triangles. And down here again, these are two similar triangles, ABC and DEF. There's the two similar triangles, ABC and DEF. Similar, but not the same. We would compare side F to side C here because they're opposite that angle there. If we double one side of a triangle, then a similar triangle will have the other sides doubled too. The corresponding sides are changed in the same ratio. Looking at this one, the side opposite X is 4. The side opposite X here is 8. So if we double 4 to 8, we must double 5 to 10 and 6 to 12. Here's one for you to do. Find the other sides in these similar triangles. That's 7, that's 10, that's 8, and this is 30. So find the other sides. Similar triangles are often useful in practical examples. So look at this example. We're going to use similar triangles to find the height of the wall. The sun is casting a shadow length B. A pole is casting a shadow length A. If we move the oh, things picking up again. If we move the pole so the two shadows line up, we have two similar triangles. W, B, S, and A, B, S2. There's a side opposite that angle, P. So we're going to compare P to W and A to B. So look at the triangles again. W over B is the same as P over A, which gives us W is BP over A. If the pole is 2 meters and we measure B as 10 meters and A as 1.5 meters, then the height of the wall W is 10 times 2, or 1.5, which is 13.4 meters. Nice, easy way of measuring heights of buildings by looking at shadows. There's nothing new about this method. In fact, it was used 2,000 years ago by a Greek scientist called Eratosthenes. He used it to measure the Earth's circumference by looking at the shadows at different points with a pole. It was very accurate in his calculations. You can look up his method on the internet. It's interesting to see. And here's a problem for you. You are 1.5 meters tall, and the sun casts a shadow from the top of a building and from you. The length of the shadow from the bottom of the building is 7 meters, and the distance of the shadow from your feet is 2 meters. I draw a diagram to show this and find the height of the building. These are also similar triangles. The triangle A, C, B is similar to the triangle Z, X, Y. And you can use these to estimate distance. There is a general rule, let's call it the rule of thumb, that when your arm is extended, the distance from your eye to your thumb is about 10 times the distance between your eyes. There we are. So we get two similar triangles, and we can use this to estimate the distance. Hold your arm straight out and put the thumb up. Close one eye and look at the object. Now close the other eye and estimate how far the thumb has moved to the left or to the right on the object. Then multiply this by 10. For example, if the object is the side of a building, which you think is 20 meters long, and you estimate that your thumb has moved about a quarter of that, say 5 meters, then the building is approximately 10 by 5 meters away, 50 meters. Remember, this is just an estimate, not an exact figure. It's useful to have an idea of the size of some objects. A car is about 5 meters long, a small house about 8 meters wide, a normal doorway about 0.8 or 800 centimeters wide. Next time you're out, try to estimate the distance between you and an object. Then place the distance out to check your findings. You can also try this at home. Stand a distance from a door and use this rule of thumb to estimate the distance from you to the door. There are several practical applications which use similar triangles. You could have a look at how they apply to a camera lens or even to spectacles. And I hope you enjoyed this little video. I think this compares or goes with the previous video I did about triangles, which I've given to my granddaughter also. Bye for now.